propensity score. Propensity score is a little different way. So this is another tool for the estimating the average treatment error effect. When there's a non-random data, so if it's a totally randomized control data, we don't need this kind of technique. So we can just simply calculate it, right? You can turn the observational data into pseudo-randomized data by applying the different weight. What does it mean? Why we cannot use our data directly? Because I don't know the count factor. But when we don't need the count factor information is when our data is totally randomized data, right? Then can we changing our non-randomized data into the randomized data? Can you do that? That's the propensity score method is trying to do. As you can see here, again, more blues, right? And more red. This is not randomized data. So if you just calculate only the red one's average and then blue one's average and calculate the difference, that's not the ATE. You are collecting some compound effect also. So the probability of x comma y when t is 0 is not the same as the probability of x on y when t equals 1. So this is like that, t equals 0. What is the probability x comma y? X plus y is a small number. Both of them are small number. Actually here, in terms of x2, this is a pretty randomized. In terms of x1, this is not 1. So if we can ignore the x2 here. Xt equals 0, so this is a t equals 0, this is t equals 1. What is the probability of x1? There is a high probability. You can, if you draw the graph, this will be the high probability in the small number, but low probability in the high number, right? And if you plot this probability when treatment is 1, so which means it's red dots, what is the probability of x1? Is this one has this shape of the distribution because we have more data, more of x1 in high. Right? So probably two of them are totally different. If this is the same, that's what we call this is the randomized sample. If this is a randomized sample, we can simply calculate the expected of y given that t equals 1 minus expected of y given the t equals 0. So we just simply collected all the t0s and all the t1s and then calculate the average and then you calculate the difference of the average. Then it can be, right, minus expected of y to y0. Then you can simply calculate the average minus average and you can get an ATE. So how can we make it's not randomized data into the randomized data? So what we're trying to do is this probability same as the other probability. So weighting means I'm gonna give a high weight. As I told you, blue dots, we have a lot of blue dots here. This side, a lot of blue dots here. So since there's a lot, so I give a pretty small weight, right? However, this side, we have a very few blue dots, right? So we give a high weight. So if we assign the high weight, what will happen is this is small weight. Assuming you have a multiple data point here, so a lot of multiple data here, then you can tell the probability of this side will become the same as the probability of the other side. So it's the same thing. This side there's a lot of red, so red will have a very small weight, but here there's only few red, so I'm giving a high weight here. So that by applying the weight, we are giving a high weight here, so it becomes similar. So what will happen here? So we defined the propensity score is the probability that t equals 1 when the given x. Right? Find any machine learning tool or such as a logistic regression, because what we are trying to do is we have to get probability. This is a probability. Propensity score is a probability. So I have to get a probability. That's why the logistic regression is the good candidate. I have to estimate the probability, right? And then sample re-weighted using the inverse propensity score. So inverse means we're going to divide the score. So what we're going to do is to calculate the ATE. We are applying, we are not simply calculate, so if we take it out, this one, no, this is not true. So I will show you what was the original formula. Right? So you divide, that's why we call this is inverse propensity score, divide by the outcome. Why dividing? As I told you, when there's a small probability, I give a high weight, right? So which means a high probability, a lot of reds here is high probability. I have to have a small weight. So when you do the inverse, high probability, small weight, low probability, high weight. How can I get a high probability, low weight, low probability, high weight? And then that's the what we do the inverse, and then we are dividing the probability as a weight. This is the weight. So when there's a high probability, divide by means you are getting a low weight. When probability is low, then you are dividing by the small number, you are getting a high weight, right? So this is the how you use calculated the estimate ATE using propensity score. This is what we call the propensity score. So using machine learning, you estimate the probability here, each individual of x, right? And then you can calculate that way, giving a different weight, and then you calculate average. Intuition of the formula, why that is working. Actually, if you think about it, the data is a really well randomized one. So when the given x, probability of t equals 1 will be the 50%, and then probability of t equals 0 will be also 50% roughly, right? So if you just apply there, so original ATE, actually this is not a ATE. You are just calculating the sum average of yi when t equals 1, and n1 is the number of data, right? T equals 1, and n0 is the number of data, t equals 0. So you have to calculate average minus average, but we use a propensity scoring here. You divide by 0.5 and you divide by 0.5, everybody has the same probability. And this 0.5 will be dividing by 0.5 is same as multiplying 2, right? So this 2 comes up here and come up here. And as you can see, n is a roughly the summation. The n is a summation of these two numbers. Roughly, what you can say is this is the same as this one. If n1 equals n2, when it's a well randomized data, you will have a similar number, right? then this one will be same as this one, and this one will be same as this one. This will be the same number. I will go over the little bit of the derivation. How we got a propensity score is actually the ATE. Average treatment effect is that we have to calculate the average over the probability of X, and you have to calculate the expected Y1 given X and minus expected Y0 given X. That's the formal definition of the average treatment effect. Again, that is not the same, this one is not the same as the expected value Y given T equals 0. This is not the same. Okay. However, we cannot calculate this one because what we have is the probability is the when t equals 1, what is the probability of x? When t equals 0, what is the probability of x, right? And then what we have is the given x, and then what is the expected of y1, and so on. So this is the same as this, right? So this is not the same, so you cannot say, you cannot replace this one to this one. That's not true. This one is not this one. So we have to adjust. Using the probability theory, you know the probability that A and B happen. It's the same as the B happen, and then given that B happen, A happen. Or A happen, and then given that A happen, what is the probability of the B happening? So using that one, you are, instead of A and B, you can replace the X given T. X is A, and B is a T equals 1. Then we can write this formula into this one. Actually, this becomes this. Both of them will be the probability that X and T equals 1, right? And then we're gonna put, because we know, this is the thing we know, right? And then what we need is the P of X. So I want to leave the Px here, and then you have to divide both sides. Is P T equals 1 given X, both sides, right? This will cancel out, only the Px left, and then this calculation will be this calculation, right? So when we do this probability or against this probability, and then you use this one, right? So you multiply this part is here, so you take it out, only I'm taking only this part and put it in here, right? Then this calculation, this multiplied this part will be the same as this one. So actually we can estimate this using this part only if I multiply this to the y. Okay, what is the probability of the t equals 1 here? Probability of t equals 1, probability of t equals 1 is the total n, again n is total number, and number of treatment 1 and number of treatment 0. So what is the probability of treatment 1 is the n1 divided by n. Out of n number of data, and one of them are treatment 1. So this is the probability calculation, and this probability calculation will be this one. And we keep this side here. And then if you take it out, this one out, right? What you're gonna have is the n. This will be what? This 1 over n1, and this comes out as n1 over n, right? So this cancel out, and this one will become 1 over n. So when this comes out together, this one, it will become 1 over n. same thing, it comes out n0 divided by, and then this divided by n comes down here, then it will becomes this one. So only these things left, and then yi we can write on the top, and this is the formula we saw. This is a propensity score estimate of the ATE. Right? This is the same as these cases. Propensity score is, so you have to estimate the propensity score, so which means we have to calculate the probability of each data point, which means we have to use a regression, logistic regression or something like that. So that estimation was wrong. Our propensity score method will be wrong. Our AT will be wrong. If there is not much overlap, the propensity score can be useless because, again, if you have a data like this, only here, and circle is only located here, there's no overlap at all, then it's not going to be accurate. You may end up with a totally opposite conclusion. And since we divide the propensity score, so when the propensity score is so really small, right, and then the weight can be really big, so that can create the large variance and large error. Because if your probability is like a 0.001 and dividing by this one, it's like you are multiplying the 1000. So when you can have a very small probability when you go to at the end of the side of the data, your probability can be very low, and you are dividing by that really small number, you can have a really big number, right? So it may create a large variance and large error. That's the drawback of the propensity score. So obviously, when we have a method that using the sum estimation, always there is a possibility you can get a really wrong answer.